Hello dear classmates, welcome back to the advanced topics. In the following videos, we are going to introduce some more advanced ATPG techniques. In this video, we are going to introduce undetect, which was discovered by Stanford to be a very effective test method. We also will introduce the cell-aware test. In the next video, we will talk about timing-aware and power-aware test. So, what is the concept of undetect test set? An undetect test set detects each fault at least n times, and every detecting pattern can be different, but it is not a required condition. This concept can be applied to any fault model such as single stopgap fault or transition delay fault. The effectiveness of undetect test set was first discovered by IBM but first published by Stanford Murphy experiment in 1995. So why is undetect very useful? Because undetect can improve our DPM by increasing the diversity of test patterns and also increase the probability to detect a model defect. The fault coverage of an undetect test set is defined in this equation. In the denominator, it's the same as before, number of total faults. However, in the numerator, is now the number of faults detected at least n times. Here is a simple example to illustrate the effectiveness of undetect test set. Suppose we have a simple circuit like this, and suppose we have a bridging defect between two wires. Suppose we apply 0011 to this simple circuit, which is a single stopgap fault test set. But this single detect test set cannot detect this bridging fault. Suppose we apply a double detect single stopgap fault test set, which is 0011, 0110. In this way, it's more likely that we can detect this bridging fault. Here is a more complicated example. Suppose we want to generate tests for wire W stopgap fault. If we consider a wire OR fault between W and the K, in this case, we would need the pattern 0 and 1. However, if we want to detect wire bridging fault N between W and K, in this case, we would need test pattern 1, 0. If we want to detect wire dominant fault between W and K, we need these two conditions. However, if we want to detect W bridging fault between power and ground, we also need different conditions. In summary, diversified test patterns help to detect different bridging fault, which can improve our DPM. So how do we generate undetect test patterns? This is an algorithm proposed by Benoit. First of all, we perform a single detect ATPG and we obtain a test set T1. And we perform a single detect fault simulation. With T1, we can obtain a fault list TFMD. So this is our target fault list. From line 3 to line 7, we have a loop to incrementally increase the number of detection. Starting from I equal to 1, we perform multiple detect fault simulation from T1 to Ti on those target fault list TFMD. And we save those faults detect exactly I times to a faultless Fi. And in this iteration, we target faultless Fi and perform single detect ATPG. And we save the patterns to Ti+1. This is one iteration. And then we continue to the next I until we generate undetect test set. Finally, out of this loop, we perform multiple detect fault simulation from T1 to Tn for all the faults, and we can obtain a multiple detect fault coverage profile, which is illustrated in the following picture. Suppose this is a fault coverage profile of T1, where F1 is the faultless containing the fault that is detected only once. F2 is the faultless containing the fault that are detected exactly twice. The vertical bar shows the number of faults. We can see the faultless of F3, F4, and F5 or more. After one iteration, we target those faults in F1, and then in the second iteration, there is no more fault in F1. So now T1 plus T2 is a 2 detect test set. So we have all the faults at least detected 2 times or more. And now we target F2 to generate ATPG test pattern. So now in the second iteration, we have this profile. T1, T2, and T3 together, they detect all the faults at least 3 times or more. So this is a 3 detect test set. So we can continue to do this to increase the number of detection. Now let's illustrate the example on this circuit. Let's consider 4 faults: A1, A stuck at 0, J stuck at 1, and K stuck at 1. Starting from the initial test set T1, we have 3 test patterns, and the detected faults are listed in the table. After the fault simulation, we know that 3 faults are detected exactly once, and the K stuck at 1 fault has been detected twice, and F3 is empty. So now in the first iteration, we target faultless F1, which has 3 faults, and we generate 2 more test patterns, P4 and P5. The detected faults are shown in this table. Now continue from the previous example. Now since all the faults has been detected at least twice, so F1 is empty, and F2 has 3 faults. F3 has 1 fault, which is K stuck at 1. So in the next iteration, our target faultless is F2. So we generate 2 more test patterns. So by now we have 7 test patterns in this 3 detect test set. And the fault coverage of this 3 detect test set is 100%, because all these 4 faults have been detected at least 3 times. Now let's see some real experimental results. Stanford performed a Murphy experiment on a 0.7 micron Murphy chip, where 5.5 thousand chips have been tested, and 116 of them were defective. As we increase the number of N, we can see that the number of test escapes decrease, which shows that undetect is very effective to improve our DPM. A similar experiment on 0.35 micron has been performed. Totally, 10,000 chips were tested and 324 of them were found to be defective. Similarly, if we increase the number of N, we can see the number of test escapes reduced. Here is another experiment performed by VLSI and the mentor graphic. In this experiment, they applied 2 detect test set, 3 detect, 4 detect, up to 5 detect test set. We can see that the number of chip failed undetect test set increased with N. So undetect has been shown to be effective. And they also show a PFA photo of a chip that failed undetect test set. A bridging defect was found to be the problem. Now it's time for you to work on this quiz. Consider these 3 faults in the circuit. After we apply these 4 test patterns, what are the 4 lists F1, F2, and F3? And what is the 2 detect single stacked fault coverage? Please now pause the video and work on this problem. Okay, so after we run fault simulation, we can show the number of detected faults. F1 contains 2 faults, C stacked 1 fault and K stacked 0 fault, which have been detected exactly once. And the F2 contains only 1 fault, L stacked 0. And there is nothing in F3. Since only 1 fault has been detected twice, so the fault coverage is 33%. Have you got it correctly? Now let's move on to the cell-aware ATPG. Undetect is a very nice technique to reduce DPM, but it has 2 major problems. First, the test length grows very quickly, almost linearly with N. As we can see from this picture, which is taken from the Murphy experiment, the test length increases almost linearly with the number of N. So if we want very effective test, the test length is too long. And the second problem is that we do not know exactly why and which defects are detected by the undetect test set. We only know that some patterns are more useful than the other patterns. But it's hard to compress this test pattern since we do not know the reason. So we need to have a better technique that can be explained. If we look back to chapter 2, our fault model, we can see that the stacked fault model and bridging fault model are mostly based on gate level fault model, which consider only the inter-cell faults. In modern technology, this may not be enough. We might want to consider those faults inside the gate or intra-cell fault model, which inspired the idea of cell-aware test. The idea of cell-aware test was proposed by Mentor Graphic in 2009. Cell-aware tests consider different defect types inside the cell, including open defect, bridging defect, and transistor defect. So for example, from this layout, we can extract many different inter-cell defects. And then we perform analog fault simulation using SPICE. Here we show an example of cell-aware test. For this MUX, which has 2 inputs and 1 control and 1 output, traditionally we need only 4 test patterns to detect a single stacked fault at the I/O pins of this MUX. So this 4 test patterns is good enough because it has 100% single stochastic fault coverage. However, if we look at the schematic and consider, let's say, a bridging defect between the input 1 and the control, if we want to detect this fault, we may need to add another pattern 000 to detect this bridging defect. So cell-aware test is effective, but it's longer than traditional single stochastic fault test. So this is a general flowchart of cell-aware test generation. Given a cell library and its layout, we perform layout extraction. We extract the fault list and run fault simulation on this schematic using SPICE. And then we would obtain a list of useful input patterns. We give this pattern to ATPG to generate cell-aware test patterns. So the fault coverage of a cell-aware test is defined in this equation. In the denominator, we consider number of total cell-aware faults. In the numerator, we consider number of detected cell-aware faults. So this is an AMD and Mentor experiment. In this experiment, totally 800,000 chips were tested, and almost 700 chips failed. Only the cell-aware test. They passed the other tests. In this Venn diagram, we can see the number of chips that fail static cell-aware test or delayed version of cell-aware test. Totally, cell-aware test can improve DPN up to 885, which is a very significant number. So, the advantage of cell-aware test is that we can reduce DPM effectively. And because we know the reason, the corresponding fault detected by cell-aware test, so it can help to diagnose our yield loss problem due to library cell. Here we show an example. Suppose we diagnose this cell-aware test failure. We can pinpoint it to a certain library that can help us to improve the yield. However, the disadvantage of cell-aware test is that the test length is longer than traditional tests, and we also need layout extraction and the SPICE simulation for many library cells. Now it's time for you to work on the quiz. Suppose the cell-aware test requires 4 different gate inputs, 0, 0, 0, 1, 1, 0, 1, 1 for the OR gate. Now please pause the video and add one more test pattern to improve the cell-aware test fault coverage. Okay, are you finished? Now, since we already have 1, 0, 0, 0, 0, 1, let's add one more test pattern. And A is 0, so our fault can be propagated to output K. Have you got it correctly? Now, in summary, in this video, we have shown 2 advanced ATPG techniques. One is undetect, which detect each fault at least n times to increase diversity of test patterns. It can effectively reduce DPN. However, the test length grows linearly with n, and we don't know exactly what's the reason for the test effectiveness. And later on, in early 2000, Mentor proposed cell-aware test. It has the advantage of knowing the reason for test effectiveness. It's very useful for diagnosis. However, the test length is still longer, and the cell library preparation is somewhat difficult because we need library extraction, and analog fault simulation. In summary, if we want to reduce DPM, we need to pay extra runtime and also extra test time. So there is no free lunch. Okay, thank you. I hope you enjoyed this video.